Okay, section 8.6, exercise 23. Again, we're determining the interval of convergence for the given power series. In this case, we're looking at n equals 0 to infinity, n factorial times x over 10 to the n. We could jump right in and take a look at the ratio test and try to ask ourselves, which values of x will yield a result in our ratio test implying convergence. I'm going to take a quick step and just kind of rewrite this a little bit so we can see more specifically, what are the coefficients on x, just by rewriting this a little bit. So we can rewrite this as n factorial over 10 to the n, x to the n. This way makes it a little more clear where we have the powers of x in our power series, and then specifically, what the coefficients look like. N factorial over 10 to the n. So let's look now at our ratio test. All right, you've seen enough of these now that we can try to be a little bit more efficient. Now we write out these expressions. I'm going to jump straight to writing it not as a ratio, but as using the invert and multiply notation. So we're going to have n plus 1 factorial over 10 to the n plus 1 times x to the n plus 1 times, and now we're going to do the reciprocal of the a sub n term. So we're going to have 10 to the n over n factorial times x to the n. So we've written this as a sub n plus 1 times 1 over a sub n. A sub n. We'll simplify here. We have all these powers of 10 in the top will cancel with all but 1 in the bottom. Same with these powers of x, all but 1 power of x in the top. And same with all these n factorials. We'll only leave the very top highest term in the factorial expression in the numerator. And so if we're careful about writing this all out, we have n plus 1 over 10 times x. And we're taking a limit as n goes to infinity. And so notice, as n goes to infinity, this parenthetical term is unbounded, shoots off to infinity. We just have a numerator that's growing, and the denominator is fixed at the number 10. And so the overall limit, well, it's almost always infinity, except in the one case when x happens to be 0, we get a limit of 0. If x is anything other than 0, this limit goes off to infinity. But if x is the number 0, we're looking at something that's growing and growing and growing, but always being multiplied by the number 0. And so while this rarely ever converges, it does converge for the single value of x equals 0. So that's the only value we can sort of plug into our original series and get a convergent series. Well, if you did the reading in section 8.6, this is what's going on when you have a radius of convergence of 0. We have no interval, we just have a single value of convergence. In this case, our radius of convergence is 0. And the interval is just a single point, so it only converges for a single value of x rather than a whole interval of values.